So today we've got Wes Whited from DNV GL. He's their senior consultant for network lighting controls, and I'd like to pass the time over to him.
Good morning, everybody.
Good morning.
Thank you all for showing up.
Easy.
So I am Wes Whited. I've been innovating in the commercial lighting markets now for about 10 years. And I was telling our friends here at Artemis Controls, when I first started in the lighting industry, my first week on the job, my boss called me into his office, told me I needed to go down to the local computer store, told me I needed to buy an iPad that had just been released that month, and a router, and my job was to hook the lights up to the internet. So little did I know that 10 years later that would all of a sudden become a career. So a little bit about myself. I sit on the Design Light Consortium's technical committee. Our job is to define what exactly is a network lighting control. And on the lighting side, I work with the IES, they're the Illuminating Engineers Society, and we're out there trying to create a standardized called technical resource manual, so all the different states' public utility commissions can calculate energy efficiency savings in the same way. A little bit about DNV GL. We're a very large, massive international engineering company. And what we do here locally is we implement energy efficiency programs on behalf of utilities like DTE. And I just wanted to give a big shout out to Sean and his crew, because last year you guys paid out about $21 million of incentives. You saved about 36 gigawatt hours of energy, and they work with over 900 different trade allies and contractors like yourself. So good job, and I know the momentum's kept up here in 2019 as well. So this is our agenda. This is what we're going to be doing up here today. We're going to spend the first bit of our time looking at a lighting market and energy savings overview. Then we're going to review 6 of the basic network lighting control strategies. At that point, we're going to break for 15 minutes and have a little bit of a network session. And then we're going to come back and we're going to talk about why you would want to source a wireless system, when you would want to source a wired system, and why you would ever look to have a hybrid of those two technologies. Then we're going to do a hard pivot there, and we're going to talk about the most important topics here today. That is the non-energy benefits that those systems produce. And we're going to spin off and talk about indoor agriculture, because that's a new use case for both LED lighting and also a new use case for these types of advanced controls. At that point, I'm going to hand the microphone back over to Mark. He's going to give you an overview of the different types of incentives that DTE is able to offer you to participate in their energy efficiency programs. So every 5 years, the DOE puts out this 1,000-page report, and they call it the Lighting Market Characterization Study. So this is a behemoth report that no one in this room has ever heard of, but I read every single word of this page, and we're going to spend a few minutes here just talking about this report. So lighting uses 17% of all electricity in the United States. So that's absolutely a huge number. And when we don't talk about electricity, we think about just energy. So that would be natural gas to heat our buildings. That would be gasoline that we put in our cars. Lighting is consuming 7% of all the energy here inside the United States. So that's the power output of about 210 coal-fired power plants, or enough energy to power about 60 million single-family homes. So lighting is a major load source for both you as a customer as well as our large investor-owned utilities. So lighting is a commodity. Don't let anyone tell you otherwise. We have about 9 billion light sources here in the United States. So just think about it. Everyone's house here, we all have lights. Look up. Every single commercial building, we have lights. Look up at industrial facilities. Look up in parking lots. Lights, artificial light sources are everywhere. And since the turn of the millennium, what we've seen is about a 20% growth in the number of light sources. But that growth has not been even. We're not really adding new lights to commercial and industrial spaces. Those new lights are really primarily being driven by the fact that we're building bigger homes here in America. So larger homes mean more lights. So the average light bulb out there in the United States right now, if we take those 8.7 billion light sources and just divide everything out, is consuming 42 watts and running for a little over 4 hours a day. So lighting is kind of the backbone of all the utility energy efficiency programs, and it's kind of been the hero of energy efficiency for about the past 20 years. So residential, 28% reduction in load since the year 2000. And that's amazing when you stop and think that we've also been adding 20% of the new bulbs that are there. A number is 40%. We saw a 40% reduction in energy use for commercial spaces. That would be buildings like this lecture hall that we have here. It's a little over 50% when we talk about our industrial facilities. Those would be our manufacturing facilities and our warehouses. And then this is the statistic that I found absolutely most fascinating. We saw about a 250% increase in energy use in outdoor lighting. Does anyone want to take a gander? What's going on here? Why is the rest of our buildings using significantly less energy, but we're using way more energy outside? And that could, oh, go ahead.
Security?
Yeah, absolutely. Not for this presentation, but for another presentation I've done, I figured out that the FBI says you're more likely to be attacked in a Walmart parking lot than about anywhere else. So, something in economics that they call the rebound effect, which is basically says the less you use something, the more new use cases you're going to find for it. So speaking, we're already using artificial lighting in our houses, in our offices, in our buildings. The only place left to really electrify would be outside. And one of the primary benefits for electrifying things outside would be for safety, security. So this is what the energy consumption of those 8.7 billion light sources look like. And I want us to first pay attention to the yellow box at the bottom, because that's LEDs. So LEDs feel like old news today. We've talked about LEDs for the past 10 years, but they're really only accounting for 8% of all the energy that's consumed out there. And the next box I really want you to pay attention to would be the ones labeled linear fluorescent. That is the most common type of lighting here in the United States. That's what we're going to find in every single office, hospital, school. And then HID lighting, and those would be our high bays and our low bays, and those are the most popular types of lighting that's found in our industrial and in our manufacturing facilities. So just two types of light sources right there make up 2/3 of all the energy consumption. And I want you to remember that, because this is where the opportunity lies as we move forward. The opportunity lies in linear, and the opportunity lies in HIDs. Today's primarily we're going to talk about network lighting controls, but I did want to spend one slide here and talk about LEDs. I'm sure everyone in this room knows the advantages of LEDs. They consume less energy. They're going to help you save money. They're more environmentally friendly because they don't contain mercury. They're what we call a directional light source, meaning they don't spill light in all directions. We can manufacture them to put the light exactly where we want. But in the context of controls, LEDs are special for two reasons. So the first reason that they're special is that 99% of commercial LED fixtures today come with a 0 to 10 volt driver, absolutely free. And so this is a humongous change compared to the ways of the old fluorescent. When I was a manufacturer's rep, you could look at something like an old fluorescent 0 to 10 volt dimming ballast from, say, Philips. That could cost as much as the entire fixture itself. It's one of the reasons why dimming was not a popular strategy. But LEDs are coming with that 0 to 10 volt driver free right now. So we're going to learn here a little bit that there's about 17 different strategies that we can use controls to save energy. Almost every single one of those control strategies will leverage that dimming driver. So having that dimming driver hooked up and ran back to an actual dimmer is incredibly important. And the second reason that LEDs are special in the context of these network lighting controls is that they're solid state technology. So it's amazing for me to tell you today that an LED light bulb has more in common with my iPhone than with the incandescent bulb that you're going to find in your grandma's house. So that's what makes them easy to pair into these digital networks. Zeros and ones, zeros and ones. The image that we're looking at up here, this is called a technology diffusion curve. The cool kids call these S-curves. So the way we read this graph is that on the y-axis, or so on our vertical axis here, this is the penetration rate of a technology. So at the very bottom, it's 0%. That says no one's bought the technology yet. At the very top, it's 100%. That means there is no substitute technology. It's the only piece of technology that you can buy. And on the x-axis here, on our horizontal axis, these are our different adopter personas. So at the very beginning, we have our innovators. Innovators are people like my father. You know, he's out there buying a VHS and a Betamax because he's hedged. He doesn't want to turn out with this thing wrong. As we move further and further and further to the right, eventually you're going to run into people like mainstream. My mom's a mainstream adopter. You know, she had a flip phone forever. She came back from the cell phone store recently with an iPhone. I was like, what's going on? I thought you liked the flip phone. She said, well, this is what the man gave me because this is all I had. So that's how we read this graph. And of course, everyone's at a different stage of the technology, kind of in between. So does anyone want to take a gander? Where do we think LED technology is going to sit here on our technology diffusion curve?
Early adopter.
You're right. Any other guess?
Early adopter.
It depends on what technology you're talking about.
You're right. You're absolutely. You sound like an accountant. So if you're a traffic signal, if you're a traffic signal, if you're an indicator light, you've reached what we would call in the utility industry market transformation. If the city of Detroit needs to go buy a new traffic light, they're not going to be able to buy a non-LED solution at this point. We move slightly down the curve a little bit when we start talking about exit signs. I think if we did a crib crawl of all the electrical distributors here in Detroit, we might be able to find a handful of old incandescent signs that are left back in our stock. But 99% of the new products that you're going to buy out there today, you're going to be buying an LED exit sign. So this is where things start to get interesting. This here is a canopy light. This represents the type of lights that we find in our exterior spaces. This particular light you're going to find in every parking garage across North America here. We see saturation rates for external LED lighting at somewhere around 30 to 40%, depending on the specific type of fixture that we're talking about. The good old A lamp, also just known as the normal light bulb, as my wife calls it. This is the most studied piece of LED technology that exists out there. We pegged this number in somewhere in the low 20%. The caveat here is the diffusion of the normal light bulb very much varies by region. So if you're in California or Massachusetts, that number is closer to 30%. If you're from West Virginia, where I grew up, the odds are you're probably in the single digits, hovering around 10 or 11%. And then this is where the graph starts to get really interesting. Remember, this is the second highest use of energy out there. This represents a high bay fixture. We're looking at market saturation rates about 10% right now. So that's saying 90% of industrial fixtures have not been converted to LED. And we move to our linear products, that number becomes 6.8%. So that's saying that there's almost 95% of the lights that would exist in commercial buildings haven't been converted to LED yet. And then when we look at the grow lights, we would use the word statistically insignificant, right? I found arguments online about whether that penetration rate was 1% or 2%. That is an academic argument. This is an example of a technology that is just kind of leaving the R&D lab and is just starting to make its way available out in the real world. And the reason why I wanted to talk about where LED technology has kind of at today here in 2019 is because, as you can see, things are about to change. I'd like everyone to raise your hand if in your facility you've converted at least some of your lights to LED. And if you don't have a facility, just sub your house. All right? So let's prove this graph right or wrong. Keep your hands up if you've converted every single light in your facility to LED. Oh, wow. So you guys are beyond the norm. So we've oversampled our energy efficient technology. But what this graph is saying is everyone who started LEDs is going to finish it here in essentially the next 10 years. And this is the opportunity, because as you begin to pair those HIDs and those linear fluorescents to LED, we need to start integrating them with network lighting controls at the same time. And that's because network lighting controls help save a significant amount of energy. So this graph right here is just showing us the savings by product type, and then the green line shows you the additional savings that the DOE assumes that you're able to get when you pair those lighting retrofits with your network lighting controls. And what we see is for the types of lighting that have the lowest levels of saturation but the highest levels of energy use, that would be our linear as number 1, and then those high bays are coming in here at number 4. The thing I really think is interesting about this chart here is screw-based lighting is another way of saying that is just the lighting that we find in our house. Is it anyone want to guess why LEDs are able to save energy in that case, but these types of commercial network lighting controls really don't save that much energy in our house?
Hours of use.
You got it. They just don't run enough. So we got 2 primary ways to save energy through a lighting retrofit. We can, on the vertical axis here, we can decrease the amount of input energy that the lighting system requires, or we can use controls to limit the amount of hours that the fixture is able to run. So So this data comes to us not from the lighting market characterization study, but from something called the CBEC survey. This is a commercial building stock survey that the Energy Information Agency puts out every 4 years. And this is the penetration rate of where controls are kind of currently at. So the most popular control strategy that's in our building today is just simple light scheduling. Most likely this is a time clock that's been in a lighting contactor panel. When we start talking about occupancy sensors, so guys like, oh, it's working. Guys like this right here, we estimate that occupancy sensors are only in about 16% of our buildings currently. And when we get to the really good stuff that saves us energy, dimming at 7%, integrating into other building systems. I met a BACnet integrator here today. We're at 4%. And the one that really astounds me is only 2% of buildings are estimated to have a daylight harvesting strategy. So this is anecdotal. I travel all around the country, but I've been in more than 98% of buildings that have windows. That just gives you an idea of the opportunity that exists here with daylighting. And we'll talk about daylighting a little bit more. It's a strategy that's really fun to talk about, but it's something that's really hard to implement correctly out into the field. And then finally, when we talk about the network lighting control systems, the reason why that we're here today, we estimate that they're only in 0.1% of all of our buildings. And the reason why I showed you this slide is I'm not here to discourage anyone. I'm actually trying to encourage everyone and saying that the future is still in front of us here, right? We are at the beginning of this journey. This is kind of a paradigm shift for the lighting industry. So with that, we are done with our market characterization study. Does anyone have any questions before we move on? All right. So let's talk about just some fundamentals of lighting controls here before we start talking about the fun technical bits about what makes our lighting system smart. So at the end of the day, a lighting control system only has two primary functions. We can switch our lights on or off, or we can dim our lights up and down. So I really struggled putting this slide together because there's actually a third way that we can interface with a lighting control system, but it's just not very popular. Does anyone want to guess what's going to be the next way, the next primary function of a lighting control system? Yeah, collar. We're going to be able to tune the collar to whatever we want as well. But that's one of those technology that's just coming out of the R&D gate, and we're going to talk about some of the non-energy benefits of collar tunable lighting here in a bit. So we're about ready to talk about the 6 most common lighting control strategies. In case you're not aware, lighting control strategy is just any different type of method or input that we use to switch or dim that light source on or off. So you're going to hear me use the word network lighting today. You might hear the word advanced lighting slip out of my mouth. You might hear me just refer to it as smart lighting. I want everyone to know that these terms are interchangeable, but we're trying to, as an industry, standardize around the word network lighting controls. So what makes a system networked or smart? So let's start with the image that I drew the big red X through. Notice that we have an LED fixture there, we have a sensor, we try to put in some wireless switches. Why is this system not smart? Well, that system's not smart because it's not about the individual pieces that make up the system, because smart lighting is much more about a system of data collection, data management, data reporting, and data visualization. So this is the most fundamental thing that we can learn here today. Our LED fixtures and our sensors, they act as data collection points. So we can collect different types of data. We can collect internal data about that lighting fixture itself. That would be its energy use. That could be the frequency of the voltage that it's consuming. And then when we talk about our sensors, they're picking up external data about our environment. That could be occupancy level data. That could be data about the light levels that exist. We're really limited by kind of what the capability of the sensor is in this point. Because we're networked, we're collecting this data, we have to do something with it. And what we do is we take that collected data and we send it to a data management system. We call our data management systems hubs or gateways. Here's an example of a hub and a gateway for this system right here. And their job is to take that data, the internal and external data that gets collected by our lighting system, and it sends it up to the cloud. So once that data comes into the cloud, it can be processed, it can be stored. It's ultimately going to get visualized on an internet-enabled device. So that's going to be on our phones or on our computers. And we can use that data to make better decisions about how to optimize our facility's energy use, as well as maybe optimize the comfort of the people that are in the building. So because this is like a fundamental slide, does anyone have any kind of questions about why we would want to collect lighting data, or what would make a network system just generally different than a traditional system that would only provide us illumination? Excellent, you guys are a smart crowd. I like it. So what makes this type of system that I brought with me here today so unique is the fact that we're able to stack these different control strategies on top of each other, which is what allows us to save a tremendous amount of energy. This occupancy sensor is super intelligent, and it's great. But can we use this occupancy sensor right here as a daylight harvesting photo cell?
No.
No, not at all. What about load shedding? No, it's just an occupancy sensor, right? It's what we would call a standalone control. So that's why the network systems that we're talking about here today are so amazing, is because they're able to aggregate all the different functionalities of these standalone controls, stack them on top of each other to go out and save a considerable amount of energy. Like I said, from an academic sense, we've identified 16 different strategies that we can use to save energy. We're not going to bore you today with all 16 of these, but I will pull out the 6 most common, and those happen to also be the 6 that will save you the most energy as you're going forward. All right, and so these are our control strategies. The first strategy we want to talk to you about today is a strategy called task tuning. Some people also call this high-end trim. Other people refer to this strategy as institutional dimming. There's no right strategy, right way to call that strategy. From there, we want to talk about scheduling. So this is the idea of just being able to turn our lights on and off. We're going to go over daylight harvesting, but just at a really high level. Daylight harvesting can probably be an entire week seminar to talk about it correctly. We're going to talk about occupancy sensing. We're also going to talk about vacancy sensing and kind of break down the difference between occupancy and vacancy. We're going to talk about the idea of personal control. When each one of our lights has its own individual IP address, then each individual person can do whatever with that lighting system that they would want, and why you would want to give people individual control. And then finally, we're going to finish up here today and talk really quickly about demand response. Demand response is not that big of an issue here in the Midwest. I live in Columbus, Ohio. We're kind of, as the utility industry would say, a wash-in capacity. But demand response is about building flexible load growth, and as we integrate more and more renewables into our mix, this is going to become an ever-growing important tool for our grid operators' tool belt. So our first fundamental strategy here today is task tuning. So task tuning means you walk to the light switch here on the wall, you turn it on, you think the light's at 100%, but some engineer in the background has really limited its output there to, say, 88%. So it's just the ability to set a maximum light output that's lower than the system's true capability. I've got this up here. This is a screenshot from the network lighting control system in my office. Setting the trim level on these advanced systems are so easy. You can see here it's just a slider. So if you set the trim level wrong and someone comes in and they say, oh, these lights are too dim, you didn't really make a mistake, because all you got to do is just pull out your iPhone and then you just raise the trim level a little bit, and congratulations, you fixed the problem. I like task tuning because it's the most underutilized strategy that I see whenever we go out and we analyze the hundreds of different applications that we get nationally. Task tuning's got a lot of advantages. So why would we want to employ this strategy? Well, the first reason is, after renovation, many of our spaces are just dramatically overlit. I was recently at a school. A school would require what they would say 30-foot candles on the work plane. A work plane is just where people are going to work. In this case, for a school, it would be the height of a desk. It's about 30 inches above the floor. The IES would say you need about 30-foot candles on the work plane. I walk in the room, we pull out our light meter, it was at 80-foot candles. So what's going on? Well, lighting designers in the past used to design for fluorescent lighting. Fluorescent lighting would quickly degrade, so it just would produce less lumens the longer that the system runs. They also suffer from what we call catastrophic failure, right? That's just a lamp burning out. So the lighting designers account for that because they're looking at what's this classroom going to be like in 2 years, not necessarily what's the classroom like the first time that you flip on the switch. This is changing with LEDs, but right, it's going to take people some time to kind of get into that thought pattern. Task tuning should be employed because it is a best practice. If you have dimmable LEDs, dim them. Dimming prolongs the life of the LED. It also saves energy. We already talked about better matching whatever that IES recommended light level is. That really helps keep people comfortable, right? We get diminishing returns when it comes to light. As we put more and more foot candles onto those work planes, we actually just produce glare. And as we produce glare, right, people start to get headaches, they don't like their space. I was up here in Michigan talking to a receptionist that was in a poorly lit space because it had too much light. She said it was making her sick at her stomach and she was calling off of work. So there are negative consequences to that. Another reason that we should look at task tuning is because people have individual needs and as well as special circumstances. So the IES would say my private office should have 30 foot candles on the work plane. I am really sensitive to light. I had a surgery in my eyes back in March. I keep my office at 5 foot candles. So if I was to follow the IES recommendations, I'm producing 6 times the amount of light that I feel was needed for me to complete my job. And the final reason that we would want to do task tuning here is this idea of lumen maintenance. And we kind of hinted on this. Old school lighting, catastrophic failure, just fails one day. With LEDs, we're going to get into the case of kind of like old mercury vapor. They shouldn't fail. That doesn't mean that they don't fail, but they just slowly degrade over time. So we call the end of life at LED as something called L70. So it just says as 30% of its initial lumens is depreciated, that's when you're supposed to go out and replace that lighting system. So if you trim your lighting, what you're doing is you're creating a bank of lumens. So as that light gets lower and lower and lower, you lift your trim, the space gets brighter. That now gives you time to plan for your next lighting retrofit. I think about this as that's the LED equivalent of the group relamping and ballasting that we used to do back in the fluorescent days. Yes, sir.
You mentioned about lights bothering people. How about, especially for schools, about flicker-free? Are you going to talk about that at all or no?
I mean, we can talk about flicker-free. You know, a lot of the times, my office actually has flicker problems right now. It's because there's incompatibility between the light and the dimmer. And that is generally the number one problem that exists right there. But flicker is really only a problem as you begin to dim down extremely low into that range, and you can always solve the flicker problem by buying a dimming ballast that it can dim down to 1%, something they call an architectural dimming ballast or architectural dimming driver. And that will reduce your problems with flicker. Then of course you need to make sure that you have compatibility between the control device and that said driver or ballast. Okay? All right. Our next fundamental strategy that we have here is this idea of time scheduling. Time scheduling is the easiest thing to understand in the entire world. We're telling the computer between 6 a.m. and 6 p.m. the lights come on. From 6 p.m. to 6 in the morning, the lights turn off. So let's think about an office space that has a time schedule but has no occupancy sensors. And Wes is working late and it's 6:01 in the evening. What's going to happen to me?
Lights going to go off.
Yeah, right, the lights are going to go off. Well, what happens at 6 a.m. and no one comes into the office? It's a Saturday. Yeah, the lights go on. So this is not the end-all, be-all of strategies, but just having a time scheduling strategy has been shown by the DOE to save about 25% energy. So this is an incredibly important strategy, and it works by creating events. So as we see up here on a calendar, we got 2 events. We got an event that's on, we got an event that's off, and the event really just determines the behavior of the light fixture, the sensors, and the switches that happen to be networked back to that system. What I like talking about with the network lighting controls is we got our old school astrological time clock right there. Historical problems with that has been around daylight savings time. We have the old school kind of plug-in timer guy right there. I use one of those for my turtle tanks. They're totally still applicable, but they're only really good for controlling a single load. And then this is the example of what the new software interfaces look like for scheduling. This comes to us, this is actually a copy of the schedule of my own office right here. We use the Digital Lumens light rule system. I don't endorse any particular product or systems. You will see different screenshots here. I've worked with different manufacturers, but at the end of the day, they're all pretty much the same. And the change here is that this is a Microsoft Outlook style calendar. So if you can set a meeting in Microsoft Outlook, then you're able to then set these events. And so this is where we can start to save tremendous amount of energy because we can create events and events. So as you see there on Thursday, I created an event inside the master event. So we can get as crazy as you want with this. I was recently with a small college up in Vermont where their schedule was those miniature events for every single day of the calendar year. And they would go to the registrar's office to determine what classrooms were going to be occupied at what times and what classrooms weren't being utilized. So, saves a lot of energy and it's incredibly convenient. One of the things that we'll keep talking about, but one of the big advantages of these network lighting control systems is not so much that they save more energy than the old types of controls, it's just that they're easier to work with, they're easier to interface with. So therefore, you're getting these additional savings because they're not set it and forget it, they're very dynamic. It's everything with the internet becomes kind of a two-way conversation. All right, daylight harvesting. I said this is the easiest strategy to talk about. It's the hardest strategy to go out and implement into the field. So it's having the lights automatically dim or turn off whenever we have natural light available in our space. Daylight harvesting is important for two reasons. The first reason is it does save a tremendous amount of energy when it's done correctly. The second reason is, as humans, we prefer the sun, right? The sun is what we would call high CRI. It renders color at 100%. Your eye naturally wants to attune to natural light, so use that light source whenever you have available. It costs you no electricity, and it's actually better for your kind of emotional and behavioral health as well. So this is how daylight harvesting works here. This is kind of, in theory, this is at a really high level. So the people in our front row, we would call those people in our primary daylighting zone. The folks that you see in the middle rows, those will be in our secondary daylighting zone. And the poor folks all the way back from the window, they're in a tertiary daylighting zone. So at the beginning of the day, at 8 o'clock in the morning, the people in our primary daylighting zone, their fixture is only coming on to 50%, right? Because it's measured at how much light do they need at their desk to complete their task. Our people in the middle row, their artificial light's a little bit higher, they're at 80%. And the people that are all the way in the back of the room, the furthest from our window, their light's running at 100%. So the sun is dynamic, right? It just doesn't just hang out low on the horizon, it goes up in the sun. So by solar noon, our people in our primary daylighting zone, they're not consuming any artificial lighting at all. They're working just off the natural light that exists there. The people in the secondary zone, their light's on only at 10%. And finally, the people in the back, their light's running at under 50%. So this is, in theory, how daylight harvesting is supposed to work. The problem with daylight harvesting, and I don't want to really get too much in it today, is where we place this sensor really matters. How this sensor is calibrated really matters. And the algorithm that controls how much, the kind of the ratio of artificial light to natural light, it really matters as well. So that's kind of the three problems that exist with daylighting. Yes, sir?
Although that would obviously save energy, isn't it hard to get it to pay for itself since you've already reduced the amount of energy that the room is going to use already because you're now on LEDs?
Yeah, exactly. So we're going to go through a case study where we look at each one of these individual strategies and as they get employed, like kind of what happens. I think of daylighting as a best practice for human beings, and we're going to get into the non-energy benefits that exist here. But yeah, you're absolutely right. LED is by far the most efficient strategy if you're looking to reduce input energy. I live in Ohio, up here in Michigan. We don't got to, mess around here. This is not California. It is cloudy here. So there is limited opportunities. But like I said, human beings, we love natural light, so we should try to use that for ourselves. It helps control some of our circadian rhythms and others. Yes, sir?
You mentioned there were three locations, calibration, the third.
The underlying algorithm that would determine the appropriate ratio from the natural light to the artificial light that would be above you.
Thank you.
No problem. Yes, sir.
You also mentioned in the previous, when scheduling was 24% savings, what would the daylight harvesting be?
It's variable, and we're going to get with that to occupancy sensing, so it's really hard to put a number on it, because it's going to vary by space. It's not only the number of windows you have, but it's the orientation of those windows to the outside. Is your building shaded by other, are you on a glass curtain tower with another glass curtain tower right next to you?
The Department of Energy, whoever gave that number for the first one, so I wasn't sure that one had a number also.
I'm unaware that the Department of Energy put that number out there, but I would assume that number would be somewhere between 10 and 15% conservatively.
That's good.
Any more questions?
I do.
Oh, yes, sir.
So, isn't it like 15 or 20 feet from the window to where it exceeds its distance for either a rebate or even catching light?
Yeah, in California, they're actually mandating daylighting now. So if you had, we'll say, a 40-foot run, that every 4 feet that you then have to integrate a new daylight harvesting photo cell. So of all the challenges that I talked to you here today, the one simple trick to make daylighting work in every type of space is to just integrate this daylighting sensor directly into the fixture. And that's going to reduce the problems of the calibration. That's also going to reduce the problems of the sensor placement. It does not change the fundamental algorithm, because that would be determined by the manufacturer. Okay?
I know it's a touchy subject with rebates, because there might be a window at the end of a hallway, and somebody's going to try and put daylight harvesting as far down the hallway as they can, just to get extra rebate money for the customer. But
Yeah, I've actually never ran into that. I spend most of my time working in California, where daylighting becomes a compliance issue for Title 24, Part 6. But one of the local people, we can follow up with you afterwards and to talk about some of the specifics of what you've seen here in Michigan, all right? So this is my favorite strategy to talk about, because I love occupancy sensors. And it's really just turning the lights on or off or dimming them down whenever there's motion or sound that's sensed in a space. From an engineering perspective, this is an override to a manual switch. The cool thing about our advanced systems is they send their occupancy sensor data back to that central server. The server then determines what the light system is able to do. So should it turn on or dim off? With the advanced systems, we have the ability to set multiple timeouts. So I should say all sensors work on a timeout. How long does the sensor need to sense no one present before it just does what it's programmed to do? With the network systems, we can set multiple timeouts. If this was a standalone control, you're just going to choose 5 minutes, 10 minutes, 60 seconds, set it up in the ceiling, and you kind of forget it. It's really hard to generalize about building codes. I was just talking to this gentleman about Title 24 out in California. The one caveat to talking about building codes in general is that most building codes across all of America right now is going to require occupancy sensors, because this is the most proven strategy to save energy. And this data comes to us from GE, and this is their estimate of energy savings here for occupancy sensors. And as you can see, it's a range, right? So for rooms that could go long periods and not be occupied, like a restroom, you might save almost 100% energy. For areas like an open office where we've got people back and forth, we save almost no energy. If I put this occupancy sensor on a 60-second timeout, that's really tight, right? It says as soon as it senses vacancy for 60 seconds, it switches the light off. If I sat underneath this occupancy sensor and did jumping jacks, how much energy would it save? Nothing, right? So it's really just fundamental to how the space is being used to determine how much energy that you can save. The average that the DOE has out there is somewhere around 20% for this particular strategy. So occupancy sensors or vacancy sensors. So a vacancy sensor means you walk into a room, you actually have to turn the lighting system on. It works on its timeout function. It sees that you're no longer in the space. It turns the light off. An occupancy sensor is always automatically on, automatically off. So it really matters the type of sensor that you're able to source. So one of the cool things about these network lighting control systems is in the software, you're able to toggle between whether you want an occupancy sensor or whether you want a vacancy sensor. If you're buying a standing load building control, if you're going down to Lowe's, let's say, you need to tell the counter, do you want a vacancy sensor or an occupancy sensor? So vacancy sensors, in every study I've ever seen, always save more energy than occupancy sensors. Does anyone want to guess why?
Because sometimes you don't want the lights on and you don't turn them on.
Yeah, that's right, absolutely. My boss has got an awesome corner office wrapped by windows. She had an occupancy sensor. She's just wasting energy. I've never seen her turn her lights on in her office. My rule of thumb here is always source a vacancy sensor if you have personal private space. If it's somebody's private office, if it's like a restroom, always choose an occupancy sensor whenever you have a shared space. No single person is in control of the switch that's there on the wall. This would be, say, like a kitchen that we're going to find in a large office complex or into an open office. We also have different types of occupancy sensors out on the market. This is what we would call passive infrared. You can pass this around if you want. Looks like a bug eye that's right there, and it works kind of like the Predator. It just senses small changes in heat, and that's how it's able to turn the lights on and off. The other types of occupancy sensors that are out in the market are what we call ultrasonic, and they work on the principle of sonar, so they're bouncing sound waves off of the walls and the surfaces to determine occupancy or vacancy. And then the final type of occupancy sensors that work today are a combination of the passive infrared and the ultrasonic. And dual tech sensors are really good because they limit the amounts of false ons as well as limit the amounts of false offs. So the problem with the passive infrared sensors is it's not really good at picking up what we call minor motion. It's you quietly sitting at your desk just typing. And with the ultrasonic sensors, if you're in a big cavernous warehouse, it doesn't work so well when you're just bouncing those sound waves off of big open space. So a dual tech sensor kind of limits the downsides of both of those different types of technology that exist there. We're going to get to when we talk about non-energy benefits here in a minute, but it's sure looking like that passive infrared sensor is going to kind of win the arms race of the occupancy sensors because it's able to do something that the ultrasonic sensor is just not capable of. All right, personal control. As I mentioned earlier, this is the idea that if every light above us has its own individual IP address, then you as the individual that's sitting underneath that light in your cube can do whatever in the heck you want with it. So it's not just having the person to have the ability to turn the light up and down or on and off as they please. It's also the ability to interface with that lighting system in the way that is most appropriate for them. My wife, she would most likely go to a website to turn her lights on or off or up and down. Some people would like a little wireless switch. You just keep this at your cube. Now you can control your light up and down. You can pass that around. The other way that we can do personal control is you can pull out the app on your phone and you can do it that way. So it's not just about you have the technical ability to control the light above your head, but are you giving the person the ability to control that light in the way that is most convenient for them?
How do you deal with the fact that one person's light doesn't only impact one person? It's still over. So in this room, say I control this light, it's going to impact all these people.
So we have an open office at my office where we have approximately 20 cubes where they have the lights. It's never been an issue that's come up. But in that case, you're going to have to just do some good old human communication and say, hey, I'm Wes and I'm very sensitive to the light and your light's impacting me. You know, would you mind dimming that down 30% for me? Yeah, well.
Typically, if it doesn't make sense to put that type of lighting in, you won't.
Yes, yeah. It only makes sense to me if you want the granular level of data. In some different types of, we'll kind of get to this, but when we build out these dense sensor networks, there's different things that we can do with the types of data that we're collecting that aren't necessarily related to the illuminating property of the lighting system as well. So the IP address is just really functional to help kind of determine exactly where to attribute that data value to. This is just kind of a side benefit of that. The final strategy we want to talk to today is this idea of demand response. And so this is, it's hard to talk to you about utility peak without having all your eyes glaze over. But the utility does have peaks. It usually happens between 4 and 6 p.m. In the summer months here in Detroit or Columbus, Ohio, where I live. And so what we see here is the blue line is just the normal baseline operations. In the red line, this is us switching or dimming our lighting loads off because it happens to coincide with utility peak. I mentioned this earlier. This is a graph from my organization puts together a very large document every year that we call the Energy Transition Outlook. So this is about a 200-page report where we really look at what is happening in the energy industry, and we project those out to 2050. And one of the things that we're really focused in on the energy transition is that we're moving away from traditional thermal, what they would call dispatchable generation. This would be coal, gas, nuclear power plants, and we're moving into a world of variable, intermittent, renewable energy. So as you can see here, we're projecting that by 2050, 70% of all the generation here in America, so this would be across every state, would be made up of just solar or wind. So as an intermittent source means the wind isn't always blowing or the sun isn't always shining. Demand response, your load as a customer now becomes a new capacity resource for the utility. We see this happening in California. I told you I live in Columbus, but I actually spend most of my working hours out in California. And this is what in California they call the duck curve. So the way that we read this is in 2012, that is what CAISO, which is the grid operator for the state of California, that is what their net load out there looked like. In 2012, California only had a small amount of renewable energy in its grid. By 2017, renewable energy made up about 30% of California's grid. What we see is a big, huge sag in the midday, right? That's solar power, all coming online at one time. And at about 3 o'clock, as the sun begins to set, we see a big, huge, steep ramp. So network lighting controls can't really do anything to shift load, right? Because we need our artificial lighting when we need our artificial lighting. But it can reduce the steepness of that ramp that exists right there. And the California Energy Commission just determined if we put a network lighting control system like this in every large business in the state of California, they could get rid of every gas peaking plant that exists out there. And gas peaking plants are expensive for the utilities to run. They have what we call low capacity factors. So it means they only run about 4% of the hours of the year. So this is just a different way to think about creating this type of flexible load. We don't always have to bring a new power plant online. Maybe we can just reduce our demand on the customer side a little bit. And the cool thing about dimming our lights, especially just lights 20 to 30%, is the human eye is very much attuned to small changes in lighting. So you can dim an LED 1-2% every 30 seconds, and the human eye is not even going to notice it. Can't do that with a thermostat, right? If we made this room 4 degrees warmer over the course of 30 minutes, everyone in here would be very angry. Or 4 degrees cooler. But we can't make small changes in lighting and basically impact the occupants in no way, shape, or form at all. So last year, when I was working on that project where we were talking about the duck curve, what we did is we modeled a typical warehouse. So our typical warehouse here used 400-watt metal halide high bays, and it operated 16 hours a day. So this is just a typical warehouse. We're going to see this in every state across North America. And so this is what our baseline power consumption looked like, right? The lighting system comes on about 5 o'clock in the morning. It's flat lines for the whole time that it's on, and then it turns itself off about 10 o'clock at night. And then where you see there between 3 and 5 o'clock, that's when the utility would most likely be out there trying to source peak power. And where it says the ramp period, that is just the amount of time to warm those plants up. And then the post-shoulder ramp is just the amount of time it takes for that system to cool itself back down. So let's talk about the strategies that we just went through, and let's see how we're able to impact this kind of customer load curve. So the first thing that we modeled is the LED lighting retrofit only. So this is why LEDs are awesome, to your point earlier, sir. We just cut that baseline power consumption 50% right there off the bat, one strategy. We also reduced our coincidence peak there by 50%. But notice the one thing that we didn't do here is we didn't change the shape of that line. All we did is just change the amount of input power that the lighting system consumed. The next strategy that we model here is we task tune those LEDs down 30%. So now we've reduced our peak demand here about 68%. So once again, we're instituting best practices of LEDs by dimming them across our institution, but we've not changed the shape of that line. The shape of that line still there stays exactly the same. The final thing that we modeled here is we put a dual-purpose occupancy sensor and daylight harvesting photocell in every one of those LED high bays that we had task tuned. We reduced consumption 93% there during peak, and notice that we pushed the shape of the line downwards. And to your point earlier, sir, you'll see just a very small sag there between 11 and noon. That was really the daylight harvesting photocell overproducing those energy savings there. And you see the line moving back down about 5 o'clock. That is the occupancy sensors overperforming and capturing vacancy as workers began to leave that facility. So this is the type of savings that we see with network lighting controls, and this is why it's a best practice to start pairing them with LEDs. With LEDs, you don't change the shape of the curve. When we start networking our LEDs in with sensors, then we're able to change the shape of that curve downward. We're able to capture the vacancy that's in the system. We're also able to harvest the sun for free energy when it's available. So that's pretty good reduction, and this is actually pretty average for projects that we see out there. We see the best types of network lighting controls energy savings coming for buildings that have very long run hours, like our manufacturing facilities and our warehouses. And on the commercial side, we see the best results for buildings that would have independent operating schedules. And that would be like your college, right? It could be 2 o'clock in the morning and your grad student could just enter the lab. So this is the last slide we have in this section. We're getting ready to go take a break. Does anyone have any questions before we go? And if you've never seen a network lighting control systems in person, please feel more than free to come down here, grab a wireless sensor or a switch, and play with the system, or I can just talk to you about it.
What were those 3 items again? Those.
Yeah, so the orange line is LED. The pink line there is when we task tune that LED, so we dim those LEDs 30% across the entire building. And then the last line there is when we put a sensor. It is both an occupancy sensor and a daylight harvesting photocell in each one of those high bays. And I didn't break it out, but the daylight harvesting photocell really overperforms when the sun was high between 11 and 1. And then the occupancy sensor really starts to predict vacancy as the workers begin to leave for the day. All right. We're kind of through the fundamentals. Let's start talking a little bit about the different types of lighting control systems that exist out there. We've already talked a little bit. The first type of lighting control is just a standalone control. The advantage of a standalone control is it's simple, it's cheap, and it's easy. The disadvantage of the standalone control is it's simple, it's cheap, and it's easy. It's a daylight harvesting photocell. It's not ever going to be anything other than a daylight harvesting photocell. The next example up there is our low voltage relay panels. We're all familiar with these. These are the way that we've traditionally done whole building lighting controls. They're very similar to our dimming or our relay distribution panels that we see in all of the buildings that we have out there. At this point, I'm just saying it's a best practice to not begin to look at them. Low voltage relay panels are efficient, they're cheap, but they just have lower levels of inputs. So you can only stack so many control strategies with these panels. They're also complex to design, so you can possibly spend more in engineering fees. We got a variety type of what I call new school lighting controls that are coming out. Standalone controls are mostly going away. But now they're just integrating these controls directly into the LED fixture. So we're just talking about a fixture that's not networked, it's not anything, it's just let's just say it's an LED strip light with an integrated photocell, or it's integrated with an occupancy sensor. Heard someone talking about program logic controllers earlier. The technical term for this technology is luminaire level lighting controls, which is a mouthful and I hate it, so I've just started calling them fixture-based distributed intelligence. So this is an idea that we're going to put a logic control, that's not even better. Hey, it's mine, okay? You come help me whiteboard. There's no easy way to describe this one. The idea here is that the system doesn't have a server that's making the decision. Each individual fixture has got its own intelligence, so it knows what its neighbor nodes are doing, and then it determines its correct sequence of operations based upon its operating environment. This very well may be the future of advanced lighting controls because they're easy, and we can actually stock these at a distributor like we would any other type of light source. Room-based controllers. I do like a whole day version of a presentation that's similar to this, and we spend a lot of time on room-based controllers. Room-based controllers are advanced lighting control systems meant for just one room. Most of the time it's just a conference room. And the cool thing about the most advanced of these room-based controllers is you can actually network them together. So this is bottom-up architecture. So you just cobble together room by room by room and build yourself a whole building advanced lighting control system. What we're going to talk about today are, because I'm in Detroit, right, this is Motor City, I'm calling them Cadillacs and Camrys. These are centralized network control systems. So from an architecture standpoint, we're talking about top down. So these systems have brains, and those brains make decisions for the things that are at the bottom of our pyramids. And as you see there at the bottom, we're back to talking about the types of fixtures that are out there collecting data, managing data, storing data, analyzing data, and ultimately visualizing data. I like the reference to Camrys and Cadillacs because at the end of the day, both of these types of network lighting control systems will get you where you need to go. Both of these types of network lighting control systems will give you all 6 of those fundamental control strategies that we talked about earlier. The difference between a Cadillac and Camry is mostly comfort level and trim level. So Camrys are more practical for most of us that are in this room, but there are people for where Cadillacs just make more sense. And we're going to spend the next little bit here talking about, is your facility a kind of facility that would benefit from a Camry system, or would your facility better benefit from a Cadillac system? So this is a fastly evolving space. I refresh this slide, it feels like every 6 months. When we talk about a Camry system, and this here is the Lutron Vive system, I grabbed this from an old employer of mine. I don't represent any product or service. I grabbed this because it fits into a suitcase, so it's very self-serving for me. It's easy for me to travel through airports and everything with. This is a Camry system. Because it's a Camry system, it's almost exclusively always a wireless system. When we talk about a Cadillac system, you can't make any sort of generalization because these systems are wired, these systems are wireless, these systems are often hybrids of both of these systems. So it's incredibly customizable to what your facility would need. Anyone in this room could be taught how to commission this system in less than a day. So it's very easy for the local agent here in Detroit or wherever to come. They might even be able to remotely start your system up. When we talk about these more complex systems, someone's flying in from the airplane from the factory themselves, and they're going to be on site for probably a week starting your system up and teaching that facility manager how to maintain that. If you want to learn how to maintain your system, you're probably flying to the factory and spending 3 to 5 days with their commissioning rep learning how to use the system. So it's incredibly complex. These types of systems, like the one I bought here today, this is for if you've got a single story in a large building downtown, or if you have a smaller standalone building. When we talk about our Camry systems, these are systems that are great for if you've got a whole building, if you've got an entire campus like University of Michigan or Michigan State, or if you're running an enterprise, your Huntington Bank, and you've got 2,000 branches across the entire country. As we talked about earlier, simplified training, anyone can learn how to maintain this system. It's very intuitive, especially as a person who's kind of okay with technology, right? I mean, the commissioning agent can basically just hand you the cell phone and you can play around with it and figure it out if you're into technology. Really not the case with the more advanced systems out there. There's one of those, if you don't know what you're doing, maybe you changed something you shouldn't have, it's very expensive to go back and figure out how to fix it. These systems always come with all the 6 basic control strategies that we talked about. When we talk about the more advanced system, you're getting all of the 16 control strategies. They're coming with native demand response, and by that I mean, from a computer science perspective, we're able to automate this demand response that I talked about earlier. So the system will automatically determine what it should do based upon a utility price signal. So the more advanced systems have that kind of interface natively built into them. They're able to monitor energy in real time at a very high accuracy level and in very granular 15-minute intervals, very similar to what the utilities meters are able to do. And then the most advanced systems out there are also going to give you an analytics layer over top that data to really help you as a facility manager determine how to make better decisions. The most advanced systems also are designed to be integrated in with other building systems. So if you own a 40-story building in downtown Detroit, you probably have a building management system as well. So these types of systems are really designed to integrate with HVAC systems, with plug loads. The most advanced systems out there right now are integrating in with video as well. So we're kind of, from an IoT perspective, we have the IoT company here, we call it a single pane of glass. Facility managers are going to have one dashboard that would allow them to control their entire smart building, regardless of what that building system is. The smaller systems, the more primarily wireless systems that we have here today, they can't be integrated into other building systems, but sometimes it's more of a challenge. They're not designed from the ground up to be integrated. Driving at home. You own that one story, you're a law firm, an accounting firm in that glass building downtown, get yourself a Camry system. You're trying to own both of those buildings, go ahead and get yourself a Cadillac. That's what those complex systems are designed for. It doesn't look like much, but this is my favorite slide in this presentation. What you're looking at here is the brand names of the 5 largest lighting control manufacturers in North America. And what we see is they all produce both Camrys and Cadillacs. It's capitalism, right? Different levels of trim and feature that exist. But one thing that I've noticed over my time working with these systems is that these simplified systems are becoming more advanced by the day. So a good example is this product used to not be able to integrate into other building systems. The second generation of this product came out, it's BACnet enabled. It's now able to. That used to be a feature of the Quantum system. So what we're seeing over time is the simplified systems are becoming more complex, and our complex systems are becoming more simplified. Maybe in 5 years, these manufacturers will offer the market just a singular product that's able to do absolutely everything. So let's switch gears here a bit, and let's talk about when we would want to use a wireless solution and when we would want to use a wired solution, and what's kind of the fundamental differences of these technologies. So a topology is just a word to describe how a communication network is arranged. So the first topology network we can talk about here today, this is just our hub and spoke. Some people call this the star model. So every node here gets attached to the node that's in the middle. And our middle node is the server, right? It's the brain. If everyone has a LAN in their house, right, this is just how hardwired systems almost always single work. And the advantage of having the server there in the middle is you can have a failure of any one of those distributed nodes, and it's not going to impact the rest of the system. So they would say that limits because of the impact of a single failure, but what happens if the server goes down? Yeah, so your whole network's down. So you can also say it's not very secure because you have a singular point of failure. So it's really dependent on what side of the equation that you're looking at right there. This type of topology will work in both hardwired and wireless networks, but it's by far the preferred topology here for wired networks. When we start talking about wireless technology, we're moving into a world of mesh networking. And so mesh is that complicated image that you see up there because every single node, and that's just a point in our network, is able to communicate with every other single node that's in that network. So there is nothing in the center. Nothing is routing that communication. These networks are self-healing. That means if that one node right there goes away, the network will automatically figure out the most efficient way to now route all of its communication between these other neighboring nodes. You could theoretically wire this in a hardwired system. It's not practical, and no one's ever going to do it. So this is really, mesh networking is only really practical in a wireless sense. And this is by far the most common topology in a wireless network. And the reason why it's the most common topology in a wired network is this guy right here is a server and a gateway, can control up to 700 devices. So that would be a fixture or any type of wireless network, sensor or switch. Because it's able to self-heal, we're able to easily add new devices to our network. We're able to easily pull old devices off of our network. So that's the big advantage, and this is why mesh networking is pretty much every wireless lighting control product that you're going to see is going to use this topology. Very simple slide here. Wireless technology works using radios, right? So something is going to transmit, something is going to receive. Wireless doesn't mean that you never use a wire. Here, our access point has got an Ethernet cable plugged into the router. The router is then what gets us up to the internet. We've got different types of wireless protocols that exist out there, right? We're all familiar with Wi-Fi. In the lighting world, we can use Wi-Fi. Oh, yes, sir.
I was talking to a couple of guys, and we were like fans would put in the lighting system for routers. They're saying that the wireless is easier to hack. So a lot of people get fancy. They want to put their wires and all that stuff together, but they want to add some kind of security system into it as well. Is that going to be an issue?
So I'm working right now. The number one problem that we're trying to solve at a very high level with network lighting controls is around cybersecurity. Quite frankly, MIT just came out with a paper last month where they were able to hack an air-gapped wired system. So the NSA has figured out how to do this. And it's because our cell phones have wireless FM transceivers, and it's able to pick up the frequency of what's running through the wires. So the answer is, I think you can hack anything if you're got the technical capabilities here in 2019. I would just say, on the back end, you just make sure your data is encrypted. It's the only thing that you could, the safest way is just to make sure that you have encryption. So if they get your data, they can't do anything with it. There's other ways. I mean, this brings up a great point, and I gave a presentation last year at a large conference. If you're looking to design a network lighting control system for your building, get your IT department involved at the absolute very beginning. One way, shape, or form, you're going out to the same internet. So whether you design them as a singular system or as separate systems, the IT department at your individual facilities need to have a say, and they need to be in the design process. They need to be in the room as if they were the MEP engineer themselves. They're just representing a fundamentally different building system. The internet in 2019 is just the same as bringing electricity into your building, bringing water or sewage into your building. It's vital. No building is going to be built without internet access. So.
Can you repeat what you said about the hacking of a wired?
Yeah, I'll send you the article. It was from MIT Journal Review.
Right.
Yeah, someone hacked a completely air-gapped system. And I'm not exactly certain how they did it. I kind of read the article on an airplane. But they used a cell phone, and they're able to figure out the frequency of what the information running through the wires. And then
Wirelessly.
Yeah, because there's an FM transceiver that's in here.
So they wirelessly were able to read wire.
Wire, yes.
Interesting.
Yeah, air gapped, and it was in like a NSA facility that they did this. So we're talking about a place that is fundamentally designed for you to not do that.
Yeah, if they're able to do it there, then what could they do here?
Yes, yeah. And quite frankly, I mean, this brings up a great point because we're at the verge of quantum computing, so maybe encryption isn't even the answer. If you had quantum computing and you had state by state, I mean, like the US government level computational power as well. So cybersecurity should scare you. It scares me. It's a big TBD in my mind. And I don't think anyone's got the answer, but the answer for your network lighting control system is to just encrypt your data is the best that you can do. It's the easiest solution. So what's better? This is probably the number one question that people ask me after these events. Do I want a wired system? Do I want a wireless system? And the answer is, it really matters. Is your project an existing building? Well, it's almost always easier to source a wireless system in that case. Is your building only exist on paper right now, with the architect or with the engineer? You can start looking at a wired solution. It doesn't really matter at that point. What's your project's budget? The knock on wireless is it costs a little bit more money up front, but studies that I've looked at says that it cuts the number of wiring termination that the electrician needs to do in the field by a third. So the product costs a little bit more in terms of bill of material, you should theoretically get a savings when it comes to the labor. So it's probably a wash at this point. We just talked about, does your user have data concerns? I used to work at Wright-Patterson Air Force Base down in Dayton. I couldn't walk in there with a wireless system. It doesn't matter what I was trying to do. That's just completely off the table. So you're going to have some customers where you just got to know your customer, right? You can't bring them a solution that they're just not ever going to be able to consider realistic. What features are you looking for? If you've got a customer that needs that full advanced feature set list, bring them a wired Cadillac system, because that's what they need. If your customer only needs the most basic features, then you're probably fine moving them towards a more simplified wireless system. And then how large is the project, right? So wires get really complicated if you've got a 40, 50 story foot building in terms of line losses. With wireless networks, they often will act as their own repeaters. So not so much of a problem there. So these are the pros and cons of both wireless and wired. Wireless is convenient. It reduces installation complexity. Has anyone here ever done a whole building lighting control system running those 0 to 10 volt low voltage cables back to a panel? It's a mess. It's a nightmare. So I was never the installer, but I was often the project manager that had to go figure out, and debug these systems on the site. It's a pain. Like I said, because of the labor, the human concern, right? We often cost much more than the bill of material, that it could totally have a lower cost. As I talked about with the mesh networking, these are easy to scale. We can add as many items as we want to the network. If we top the list of 700 devices for that server right there, all we need to do is just go buy another server, and then we can add 700 more devices to it. Wireless systems go in a little bit quicker, so if you're trying to retrofit this building on the fly, you're going to see less disruption to your building occupants. You're not trying to be up in the plenum as often. And then you can actually add connectivity to spaces where it's physically hard to access. That's very important in industrial facilities. These sensors here supposedly have a 10-year battery life. So you can put this sensor somewhere where it's just because a conduit runs, you don't want to go and hardwire something back in. We've got some downside. Reliability. All networks will fail. So even if it's a mesh network, it's self-healing, you have to build in the fact that it could possibly fail. But like I said, by the fact that these are self-healing, it really simplifies that problem. You can always get interference when it comes to wireless devices, and if you're using a very popular band, like the 2.4 gig that Wi-Fi is on, then you're going to have a greater chance of interference. I'll tell you, one of the biggest professional mistakes I ever made in my entire career is I put a bunch of wireless lighting controls in a fire station in Columbus, and it messed with their walkie-talkie system. Does anyone guess what happened to my design? What do you think the firefighters chose, right? Did they choose the ability to dispatch the firefighters or save some energy? Right, so we just talked about it. Great question right there. Security. Wireless systems are easier to hack, right? Because it's not just flowing through wires that are air gapped up in our ceiling. The information is just kind of floating all around us. And so if you have a gateway, and we have gateways, we're all walking around with a Wi-Fi gateway right here. We're all walking around with a Bluetooth gateway right here. These systems are easier to hack. And then wireless data transfer is a little bit slower than wired. So what's the advantages of having a hardwired system? Discounting the MIT article that I just told you about, they're theoretically will prevent unauthorized access to that network. They have faster data transfer speeds. Incredibly reliable. Reliable until you have a cable failure, and then you have a big problem. So possibly cheaper when we're looking at just the bill of material cost. But anytime we have a hardwired system, we got something wired in place. So if we want to add a new device, we got to run more wire. If we want to take an old device off the network, we need to pull that old wire. Increased project complexity, as well as you've got to have some additional project setup. Yes, sir. Oh, not self-healing, right? So the idea of your cable's damaged, you're pretty much done. And then this can be disruptive to building occupants because it is just more complex because you're up running all that additional wiring. So what's the winner? I took a accounting class, and the CPA taught my class. Every question I ever asked him, he just said, it depends, it depends, it depends. And this is the case when it comes to wired or wireless or even hybrid systems. Because it's what stage is your building is really the first question that I think you need to ask. If you've got an existing building, wireless systems are probably going to make the most sense for you. If, like I said, if it's on paper, it's in the design phase, then you can have any type of system that you want. You really have no constraints at that point. You know, how big is your building? Wired systems, there are line losses. Mesh networks are easy to add because they act as repeaters. How important reliability is to your customer? Maybe that's the first question that you really need to go and ask. I was with a lighting designer that designed a big building for Goldman Sachs. I was like, did you talk to Goldman about wireless? He's like, no, man, that would have just wasted months in our design phase. I knew exactly what they needed because they're a bank, and data security is of more importance to them than anything else. And then that's the other question is, how important is security? You're going to have customers out there like the United States government, like our large investment banks, where data security is going to be their top concern regardless. So, you know, the final verdict, I would choose a wireless system for 99% of the projects that exist out there today. I would do the wired for when I've got incredibly complex customers. I have customers with unique needs. I have customers with a higher budget that want a totally, engineered solution. So that's kind of where we're at right there. Before we start talking about non-energy impacts, and that's just the value that these systems can create outside of energy savings. Does anyone have any questions about networking in terms of wireless or wired communications? Yes, sir.
What is a length, distance you can communicate with your gateway and the devices?
I would depend on the protocol specific. So for something like Bluetooth, the downside to Bluetooth is that I think it's at like 10 feet, but it gives you accuracy if you're trying to locate a device to within centimeters.
No, I'm talking about like the placement of one in a large facility to reach the maximum amount of fixtures. The protocol would be Zigbee.
I don't think I'm following. Are you talking about where you place the server? Because this is 700 devices or up to a 700-foot radius.
Oh, that's what I was looking
Yes.
at. The radius.
So if the device falls outside the radius of that and you haven't reached the theoretical cap, you're still going to need to source a second server just to get that connectivity. And the radius is going to be product specific. So I know this particular product, I talked to the product designer. They designed this to basically work for one floor of a large building. So that's how they came up with their 700-foot radius. They probably crunched a lot of data and said that this is about what one floor of a building would be.
Line of sight.
Yes.
So a constraint is distance.
Yeah.
Is that system centralized?
Yes. It's both a server and a gateway.
Gotcha. So every device has to be within range of that specific
Yes, sir.
gateway. But it changes if you're in a mesh network.
Yeah. And it uses a proprietary protocol. This particular manufacturer bought a subband from the FCC. They call it Clear Connect. Yes, sir.
So like on mesh networks, do those have repeaters that extend the signal?
Theoretically, every device connected to the network should be its own repeater. But I think that depends on the protocol, but I'm not exactly certain off the top of my head. All right, this is my favorite subject to talk about here. And this gentleman and I were speaking earlier, and it's all well and good. These systems are great for the environment. They save a lot of energy. But you can have some uncomfortable conversations with CFOs about the value that these systems produce. And so non-energy impactors are all the different value that these lighting control systems can bring to an organization outside of energy savings. And this represents the pathway that helps lower some of those hurdles for our financial decision makers. Has anyone here heard of the 300 rule? Yeah. So Jones Lang Lazare came up with this rule a few years ago. And the way that we read this rule is a typical business here in North America pays $3 a square foot annually for their utilities, pays $30 a square foot for their rent, and is paying $300 a square foot for their payroll. I like to think about this in the backwards. So if my lighting control system right here can increase a worker's productivity just 1%, I've now increased and created as much value for that organization as all of that project's potential energy savings. If my networked lighting control system can help a facility manager or an office manager make their space 10% more efficient, I've now created as much value for that organization as all the potential utility savings that could exist. So the financial gatekeepers of organizations, they are basically driven by creating organizational value. When they're out deploying their capital, that's one thing that this gentleman and I forgot to talk about. Lighting control systems, lighting in general, always used to come out of the operating budget of the facility manager. We're now talking about millions of dollars for some of these systems and some of the lighting upgrades. Now this becomes a capital project for that organization. And when you are a capital project for that organization, you're competing for the limited capital of that organization. So you need to do a little bit more of an energy savings, in my opinion, as a person who's been charged with out and tried to sell these types of systems in a business development role. So what is the future of these lightings? We talked that the big paradigm shift here is that they're producing value beyond illumination. So what can we use this data that we're collecting for? How do we use this data to create additional value for organizations out there? This is a graph that some smart engineers at my company and myself put together last year. On the vertical axis, we talked about here is what do we see as the business value? Is it producing kind of low value? Low here would just be, in terms of, is it going to create revenue for the company? And then on the horizontal axis is the maturity level of where we see this technology. And the three that I have in yellow are the three that we're going to talk about here today. Some of them are what I consider a mature technology. And by mature, I mean you could buy it today off the shelf. It doesn't mean that it's been tested because a lot of this stuff is still new. And by emerging, I mean you're going to be an innovator on our S-curve because you're going to be buying a system that's basically been market unproven. But you're doing that because you're theoretically going to be able to produce higher value for your organization. Predictive maintenance is this idea that we can use data to quantify the probability of a failure before it happens. Maintenance today is largely reactive. Is anyone in this room a facilities manager? Would you think, is that a fair characterization? Yeah, you're responding to alarms and bells. You're not out there, proactively trying to, fix problems. And that's not an issue with our facilities managers. That's an issue with our building systems not providing them the data that they need to make their decisions. When we talk about creating business value, what we're talking about here is uptime, right? This is very important for businesses. Am I able to utilize my asset all the time? Because if my machine is down, if my lighting system is off, then work is not getting done. It has an opportunity cost for that organization out there. It is unsafe, especially in industrial facilities, when lighting systems go down. I was at a facility in Columbus, Ohio, where I live. They're smelting glass, and I would say every third light in that facility is just off. I didn't have a light meter with me that day. Like I said, I like it dark, and I found it dark. I would not want to be around the machine that's pulling the molten sand, in an environment like that. But it's going to lead to lower labor and material cost if we move to this predictive maintenance type of strategy, because instead of scrambling, once the machine is broken, then facilities managers have to go to the local electrical distributor or whoever. They got to source their parts, and then they go back and fix them. If we know something's going to break beforehand, then we just order the part from the manufacturer, normally at a lower cost, and we can install it at our own convenience. And the final bit I want to talk about here is just this idea of improved aesthetics. Aesthetics mean a lot to a business. I don't care if you're a successful business. If you walk in and you're at the receptionist and the lights are burnt out, you're going to think that that business is not that attractive, even if that is just not the case at all. Maybe they just happen to have a random failure. So aesthetics are very important to some businesses. This is an example of a predictive maintenance system that exists today. This is a system from what are they? They're Dutch, and they're called NeedApp. But this is kind of what I think about as the future of facilities management. Your system, you're a facilities manager, you log in, it's giving you an action list that day for what the system is telling you needs to be done. It's telling us that in this one particular facility, they've not tested the emergency lights in these batteries. So if you go and you schedule those lights, it will do it for you remotely and then mark it in an Excel sheet. So if you have an audit of your facility, the fire marshal comes through, you just then hand the fire marshal that Excel sheet file and says, look, every 90 days we're in compliance, or whatever your local building code would happen to be. It's telling the facility manager that they need to visually inspect 73 lights, right? That's the system, that machine learning algorithm in the background saying that there could possibly be a problem here, but we don't know what the problem is. I need to dispatch a human to determine maybe it's like a crack in a housing or something. And then it's telling them that 28 lights actually require maintenance. And if you go and click on that button that says view logbook, it will tell you the specific error. Most likely, 99% of the time, LEDs do not fail in terms of the chipset. It's almost exclusively a driver issue. And so this would tell that facility manager that I need to order 28 additional LED drivers from said manufacturer. So this is just a different way of thinking about facilities management. And this is one of the big advantages of having a network lighting control system, is that you're collecting this data, we're adding that analytics layer on top of it, and we're helping our facilities managers proactively solve their problems, increase the uptime, and that's got business value for our CFOs, our CEOs, and the type of people that are charged with producing value for their shareholders. This is my favorite subject to talk about. We did a study last year of the largest lighting manufacturer here in North America, and I got to speak to every single one of the regional sales managers. And we looked at 5 different technologies, and we asked these sales managers, what did they see as the #1 technology in providing value to their customers, but what did they see as also they had to provide a value of what their own personal knowledge was. And when it came to circadian rhythm, almost everyone gave us a 10 in terms of potential value, and some people were giving us negative values for their own personal value. So there's a large gap there between people's knowledge of this technology and where they think the technology can go. Personally, I'm sold this is the future of lighting here. 2 years ago, CBRE did a case study where they put color tunable lighting in one of their offices. They found that 71% of the people that participated in this study felt more energized. About 75% of them felt happier. Heck, 50% of them felt healthier. And this really matters because we spend a heck of a lot of time indoors. Lawrence Berkeley National Labs say 90% of our time in enclosed spaces. The idea of circadian lighting is we're trying to, as you can see it from this image, we're trying to mimic what the sun is doing outside, inside. And that has a large effect on our biorhythms. And it really does have an impact on our health and on our behaviors. We've got a couple case studies that exist out there. The DOE did one in Washington State. It was like a psych ward. And what they found was that the number of incidences of people needing to be medicated was down something like 20 to 30%. There's another case study that happened in the Netherlands, I want to say, where they were people who had sundowners, a certain type of Alzheimer's, where they're very sensitive in terms of their circadian rhythms. They were able to reduce the average number of medication a patient got by something like by 3 pills a day. So our bodies are attuned. We've evolved for millions of years to react to the sun cycle, and by spending a lot of time indoors, we are basically cutting ourselves off from that biorhythm. This is just what it looks like. It's not just, this is the hard part of circadian lighting. It's not just about having the color temperature change throughout the course of the day. Think about the sun. It also becomes different levels of intensity. So, We got, from a controls perspective, the sequence of operations on these things are nuts, because we need to make sure that we're mimicking the correct color of the sun at the correct time of day. We also need to mimic its correct intensity. In the education setting, the studies that we're reading out there show that children that are exposed to the color-tunable lighting are able to read at faster levels. They're also able to recall a little bit better. One thing that we know for certain, there's not enough research here. This is like literally an emerging technology. But one thing that we do know is that warmer color temperatures at lower intensity levels help us relax. I'm sure we've all been to a brew pub here where they're dangling the Edison-style bulb and it's kind of dark and it's orange. They're doing that for a reason, right? Our restaurant lighting designers have figured this out. As we move to the 6500K, the more white or blue light, that has really been shown to increase our attentiveness. And especially increases our attentiveness when we increase the intensity. So from an energy efficiency perspective, there's a big debate right now about whether circadian lighting is energy efficient. Because there are times a day where you're going to be putting more light on the work plane than is theoretically required, because you're trying to jumpstart someone's biology. So, does that mean that the lighting system is inefficient? The 3-300 rule would say no, because if you're making 76% of the people happier, you're actually helping them focus more, and they're creating more value for the organization relative to the additional marginal amount of energy that you produced. But that's just my opinion. This also opens up a great conversation. I'm sure everyone here has read an article about don't look at your iPhone at night because of blue wave light. So there's a lot of debate right now about whether short blue wave light is good or bad for your circadian health. And the answer is I've read studies both ways to say that yes, it is, and no, that it isn't. So this is an area that is really complex because we're now blending physics in with electrical engineering, in with neuroscience. And there's like 2 people in the world that are basically PhD level neuroscientists that also have a background in electrical engineering. So. Does anyone have any questions about circadian lighting? I'll try my best to answer any that you may have. Emerging technology, totally the future. This is probably 20 years off. That you can buy the products today, but this is not going to mainstream for a while. Remember earlier I told you that we had different types of occupancy sensors? And that I thought the winner was going to be this passive infrared sensor. This is why. This is the idea of space optimization. And this right here is just a typical office space. And the only thing that this lighting sensor is doing here is it's just streaming its data live over an app. So this is the same data that it would use to switch the lighting system on or off. And it catalogs where and how people are moving around this space. In some of the space optimization studies I've been reading, something like conference rooms are actually only utilized 10% of the time. Smart companies are out there actually breaking down their conference rooms and their pull-out rooms and turning them into private offices. IBM used this strategy, was able to reduce the amount of floors that they rented in their Manhattan office by 2. So I don't know what it costs to rent a floor of an office building in lower Manhattan, but they probably found some significant savings there. So this is an example of how a lighting control system can improve the productivity of a space. And remember, that's about 10 times more valuable to your average organization out there than just the energy savings alone. When we talk about the circadian health, when we talk about the space optimization, we're actually producing so much value for that organization that the energy savings are just kind of coming along on the tail end. It's really not the story that we're telling. Yes, sir.
See on the screen there.
This is how people move around. So the red areas would be the hottest areas where people are moving the most. The blue areas would be when people had left for another period of time. Green just means basically no activity. And it must be lunchtime in this visualization because the kitchen seems to be really popular. People are kind of exiting cube land. No one goes in the conference rooms in this particular. The other thing that we could talk about here, it's a slightly different strategy. It's the idea that instead of trying to see how people move around the space, we can track how assets move around this space through the use of Bluetooth beacons. And I've been working with a company that is doing this, and they're providing shopping analytics to retail stores. So I don't know if everyone's heard, we're supposedly in a retail apocalypse. This is a very, very hard time to be like a traditional retailer. So they're figuring out how their customers are moving around their stores to best determine where to place the merchandise that's going to help them make the most money. So that's just an example of kind of creating that additional value. Who would have ever thought an occupancy sensor that switches the lights on or off could be used to do that? But this is the power of that data connectivity. This is kind of that fundamental paradigm shift. And this is what the CFOs really want to see in my mind, not so much just the report of what you're going to save in terms of the energy. Do we have anyone here today from a vertical farm? I'm really excited. I'm going next week and speaking at this place called the Energy World Congress, and I'm talking about indoor vertical farming. In Michigan, like, you guys are the leader of this technology right now, like here in terms of the Midwest. It's almost growing, yeah. It's a little skewed here in terms of the types of plants that people are growing indoors. We grow a lot of tomatoes indoors in the Netherlands. I don't want to talk about the types of plants that could be theoretically grown indoors here in Michigan, but there's some serious energy implications, like when it comes to vertical farming, whether it's stacked farming or non-stacked farming. It could also just be if you have a greenhouse where you're providing supplemental lighting and heat to extend your growing season. A lot of different words. The DE, the DOE, they prefer controlled indoor agriculture. I like the word plant factories. But it's the idea of taking an existing space, like a warehouse space. I've seen these in old strip malls where they're growing food indoors without natural light. So almost everything exists today in kind of the 2D world. In terms of us human beings, but with the plants we can actually go and grow in cubic space because we can vertically stack it and grow up. Contrary to popular belief, we can grow any plant that we want indoors. And some of the studies from the plants out there that are being grown indoors is absolutely amazing. 350 times more productive per acre on 1% of the water resource. So if you're in California, if you're in Saudi Arabia, if you're in Dubai, water scarcity is a real thing. So not only are you getting increased yield by hundreds of %, but you're using a fraction of the inputs. This comes to us from Stanford. And what they did is they wanted to look at the market potential. So like, where is the potential for indoor farms? And the commonality that I can tell you that exists in this graph that you're looking at up here is places that have high populations that also have high GDP or high incomes. So the largest market potential resides in places like Tokyo and New York. The reason why we talk about cannabis when we talk about indoor ag is when I was pulling data to put together my paper, I found 7,865 data records for marijuana producers here in the United States, and I found 15 data records for everyone else. So a data set is slightly skewed there. I don't even know what that percent would be. But there is energy implementation when it comes to growing any type of our plants here indoors. And the lighting implementation is actually huge. So this comes to us from the utility in Portland, Oregon called the Energy Trust of Oregon. They own the largest data set when it comes to growing cannabis indoors. And 55% of that energy consumption comes to us just from the lighting. The way that I like to think about this as an energy engineer is that this is the flip of a data center. So in a data center, the HVAC is producing the largest load and the lighting is the smaller load. This is kind of the inverse of a data center. We've been starting to talk to different growers out there. There's a lot of different myths that LED lighting is somehow bad for plants. LED lighting produces less heat, right? If you look at something like those old metal halides, they get very warm. You can't stack them because you'll just burn the tops of the plants. So if you want to grow in a cubic environment, good luck doing it without LEDs. And that's the conversation that we're starting to have with these folks. And what we see here is that they consume far less energy on a square foot basis than their other light sources. And this matters because I told you earlier, if you're here looking to retrofit your facility to LEDs and controls, you're going to get your highest paybacks when your facilities run a long time. Well, if you're in the clone stage, your facility's running 24 hours a day. If If your facility is in the vegetative stage, you're running about 16 to 18 hours a day. And when you're in the flowering stage, you're running 12 hours a day. And each of these operations have thousands of plants usually in each of these different stages. So these are massive energy consumers. When they first legalized cannabis in Oregon, they had 7 brownouts from people bringing these facilities onto the grid. Yeah, I mean, we laugh, but I mean, there's like serious energy implications here. And switching to LED lighting is going to not only produce more yield per gram, so there's what we would call a process efficiency to using LED, but it uses approximately 40 to 45% less energy as well. So this is why it matters. Data centers, largest energy consumers out there in the United States. Look at this, cannabis cultivation. This has only been around for just a few years. It's already our 3rd largest source. And it's twice the consumption right now. EVs get all the what we would call road growth in the utility industry. This is what they're all talking about. But really right now, just to grow plants indoors is consuming twice the amount of energy as all the EVs when they're plugged into the grid. And that number is forecasted to grow 126% year over year right now. So all the way out to 2025 when it probably will start to flatline. So one of my principal engineers and myself, he was out in Las Vegas. We did a case study and we wrote a white paper on color tunable LEDs in these plant factory settings, and we used what the facility had as an existing. So they used 1,000-watt high pressure sodium lamps. This is kind of the industry standard when it comes to growing cannabis indoors. And like I said, we retrofitted this facility with an equal number of color tunable LED fixtures. And what we found was at the end of the day, there was a 41% energy reduction. The LED fixtures produced 6% higher gram per yield than the HID fixtures. And this facility was able to lower its peak demand an additional 20%. So that's significant. Energy consumption for an indoor farm is the 2nd highest operating expense outside of their labor. So it's something like maybe 25 to 35% of their OPEX. So dropping that by about 50% is absolutely humongous. And the fact that they're growing gold or oil or whatever, 6% extra of their product is actually kind of huge for them on the backside as well. Yeah. And then obviously in terms of utility bills, peak demand, especially this was a Western state, and this customer was on more of a critical peak pricing model. So by lowering their peak demand, they actually got lowered that OPEX even more than just the rote KWH number, which is just a measure of total consumption. So that's what I have prepared here for y'all today. Thank you guys for your attendance. I'm going to turn things back over to Mark.